Hey y'all, welcome back. So today we're just going to continue to practice graphing these rational functions. These particular notes are going to be something that I want you to do independently. So I'm going to run through this pretty quickly and let this video just serve as a resource in case you get stuck. This is not going to be like one of our normal lecture videos where I'm explaining a new concept, but rather just kind of going through these and giving you an opportunity to look and see if there's any problems that you're just not really understanding on your own or don't get your questions answered in class. So like I said, we're not going to really go over anything new today. It's really just going to hopefully put together what we've learned in this unit so far. So for number one, we are tasked with making a table of the parent rational function, which is like pretty much the most basic kind of rational function you can come up with, 1 over x. And instead of plotting it like we did in the last lesson, we're going to construct a table and then plot the points and then make sure that it actually fits what we would have found otherwise. So if I plug in -3 here, I'm going to get -1/3. If I plug in -2, I'm going to get -1/2 and so forth. So coming up with these values should not be too bad because it's just 1 over x. It's not like you're really doing any computations here. So I get -1/2 if I plug in -1. I'm just going to get 1 over -1, which is -1. If I plug in -1/2, now this might be the only place where it gets a little tricky, but if I plug in -1/2 here, I get 1 divided by -1/2, so that'd be -2. 1 divided by -1/3 is -3. 1 divided by 0 is undefined, so that's going to be where our vertical asymptote is. If I plug in 1/3, I'm going to get +3. If I plug in 1/2, I'm going to get +2. If I plug in 1, I'm going to get just 1. And if I plug in 2, I'm going to get 1/2. That looks like we got one more. If I plug in 3, I'll get 1/3. So these are all going to be coordinates that we're going to plot on that grid and kind of see what the parent rational function is going to look like. So we'll start up here at the top. -3 is going to be over here. -1/3. So this grid, it doesn't really lend itself very nicely to thirds. But like right here, it would be like 0.2. This is 0.4. So it'd be somewhere in between there. I'm just going to estimate that it's right about here. Not a square. Let's get a circle going here. So it'll be roughly right in here. So if I, come on, there we go. If I, so -2, -1/2 is going to be right about here. -1, oh wait, negative. Oh, already making mistakes here. Come on, Mr. Schuler, get it together here. Yeah, we should be below the x-axis here. -1, -1 is going to be here. -1/2, -2 is going to be here. And we're seeing some symmetry here, which should be to be expected. -1/3, -3 should be roughly here. And let's see, is this pointing in the right place? No, there should be -2, -1. Oh, wait a minute. -2, -1/2. Somehow this point got way off. All right, so there we go. Here is the left-hand curve. We can see that we can kind of tell what's going on with the horizontal asymptote, even though we haven't really broken it down. It appears as though the horizontal asymptote is going to be y = 0, which makes sense because the degree of the denominator is larger. Here we go. A little sloppy, but you can kind of see what the grid is doing here. Now at 0, it's undefined, and that's because we have a vertical asymptote. Let me zoom out a little bit so we can see this a little easier. We've got a vertical asymptote going on along that y-axis. Oh, okay. All right. Getting a little crazy here. Slow and steady. All right, now on the right side of the graph, we should get basically the same image here, except it'll be flipped. I wonder if I can do that. Let's just see if I can save myself a little bit of time here. Is this gonna? No, it's not gonna let me revolve this. Okay, so that's okay. We'll just replot the points. what's the fact? Here we go. Okay. So the first point should be at 1/3, comma 1. I'm sorry, 1/3, comma 3. So it's going to be roughly here. And then the next one is at 1/2, comma 2. And then 1, comma 1. So you are seeing this symmetry about the origin. Let's see, 1, comma 1, 2, comma 1/2, and then 3, comma 1/3. All right, so you can kind of see what's going on here. We've got a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. So this is what the parent rational function looks like. If I can make it through all these points, there we go. Always tricky with this mouse. But all right, so we've got this graph here. So let's see if we can answer the follow-up questions. The first one's what's the domain of the function? And the domain's going to be all real numbers except where the function's undefined. So that would include both vertical asymptotes and holes. We don't have any holes here because there are no values that'll make the numerator 0. So the domain's going to be all real numbers except for 0. So you could just say x not 0 is probably the most efficient way to write that is as an inequality. If you want to write it using set notation, you would say from -infinity to 0, union 0 to infinity. The range is going to be the same. Everything except for 0 is going to be defined for the y values. So I can say y cannot be 0. Or you could say that y is all the values between -infinity to 0 and 0 to infinity. Now the next couple of follow-up questions here say, what happens to the function when x gets close to 0? Well, as x gets close to 0, the function either goes to -infinity or +infinity, depending on how you are approaching the vertical asymptote. So we can say something like, as x approaches 0 from the left, y approaches -infinity. Let's see here, let me grab an infinity symbol. Okay. Okay. So, as x approaches 0 from the right, y approaches +infinity. And this is kind of gets to the whole reason why we can't divide by 0 or why it's undefined is because if we approach 0 from the left and the right, the value of this function is not approaching a specific value, and it's not going both to infinity on either side. It's actually going off into two different directions, right? So it's not going to be clearly defined what 1 divided by 0 is. All right, the next question says, what happens to the value, what happens to the function as x gets very large or as x approaches infinity? Well, we can say that as x approaches infinity, the function's value approaches 0. So we can say as x approaches infinity, y approaches, or f of x approaches 0. And I cannot spell apparently. Now, as x approaches -infinity, it should also approach that horizontal asymptote. So as x approaches -infinity, y also approaches 0. So this should be, now you don't have to answer this word for word, but I do want you to be thinking about what's going on with the function as x goes to infinity, -infinity, and what's happening as x approaches the vertical asymptote. All right, so now we're getting into the kind of the meat of it. This is going to be more along the lines of what we did in the last lesson. So this is really just going to be practice here, practice factoring, practice going through all the different component characteristics and so forth. So the numerator here gets factored as x minus 5 times x plus 4. And the denominator gets factored as x minus 2 times x plus 1. So I'm looking at these factors. I notice there's no holes here. So I'm going to have two x-intercepts and two vertical asymptotes. So to write this in factored form, I guess I kind of already did that. F of x equals this up here should be the numerator. And then this should be the denominator. Okay, so the domain here is going to be everywhere except where the function's undefined. So there's two ways you can write it, and I'm going to go ahead and just show you both ways. I think the domain is probably easier to write as an inequality when it's all real numbers except for two values here, which would be at 2 and -1. But if you wanted to write it using interval notation, you would say x is an element of, I'm going to have to grab that element symbol. And then we'd say -infinity to -1 union -1 to 2 union 2 to infinity. So you can see pretty clearly that the inequality way of writing this domain is going to be a much simpler way to write this. And you know, I think I might even put the -1 first here, just so you can see a little bit easier. So it's basically all real numbers except for where it's undefined. You know, sometimes it's just easier to describe something by saying what it's not rather than what it is. If you're saying it's everything except these two numbers, it's a little more efficient way of writing it than just actually listing out all the values. Give the equations of any vertical asymptotes and sketch them as dashed lines. So dashed lines will be good, like if you're handwriting this using a pencil or pen, or if you have different colors, or like what I'm going to do here is just use a different color to do the vertical asymptotes. But those vertical asymptotes are going to be at -1 and at 2. So I'm going to go ahead and draw those out. So at -1, we got a vertical asymptote. And at 2. The next question says, give it the equation of any horizontal asymptote. Well, since the degrees here are the same, we're going to look at the leading coefficients, which are 1 over 1. So my horizontal asymptote is just going to be y equals 1. And I'm going to sketch that right here. Again, it says a dashed line, which is a good idea if you're doing it by hand. It's like just using one color, but if you have multiple colors, you can just change the color to make, basically what you're trying to do is indicate that these are not points that are solutions to the equation, but rather they're asymptotes. Find the x-intercepts and clearly show on the graph. Well, we can see from the numerator here that we're going to have an x-intercept at 5 and one at -4. So let me go ahead and write that here. 5, 0, and I think the other one was -4. Is that what I said? I'll double check, but I think it was -4. Yes. And clearly show them on the graph. So we will go ahead and plot those 2 points. So we've got one right here. And we've got one right here. Okay, find the y-intercept. So the y-intercept is going to be when we plug in 0 for all these. So if we do that, if we've got 0 here, 0 here, 0 here, 0 here, we've got -20 over -2, which when you divide that, you get 10. So the y-intercept is actually way, 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 way up here. Kind of interesting. This is going to be a pretty extreme drop here in between these two asymptotes. So yeah, we do get y equals 10. The way we're going to write that, though, is as a coordinate, 0, 10. And we can see it right there. Okay, so complete the nice sketch. Okay, so basically now we're just going to kind of fill in the gaps here. We know that this function should approach the asymptote, so we should get a graph that kind of looks like this. So here's the first piece. Here's the second piece. This should go down and come back up. We're not really sure where this relative minimum is. You know, maybe further up here, maybe lower. We know it's not going to cross over the x-axis, so it's not going to come down here. But for now, we're just going to kind of sketch it out. Next year in calculus, you'll figure out how to find these relative extremes. So, and then the last one's going to look like this. All right, so there's the graph of number 2. Now let's take a look at the next one, number 3. Okay, so first we need to go ahead and factor this. So we've got to come up with a couple of factors here. Let's see, we got f of x equals, so it looks like the numerator is going to have a 2x and an x. So it looks like it's going to be 2x plus 3 times x minus 1, right? So that would be like negative 2x plus 3x adds up to positive x. So that should work. And then for the denominator, it should be 4x plus 1 and x minus 1. That should work out too. All right, so we are going to have a hole here. We do have a hole at x equals 1, so just be on the lookout for that. The domain here is going to be everything except for the values that make the denominator 0. So I'm just going to opt to use the inequality way. So I'm going to write it kind of like this rather than like this. So not using the set notation. So my domain is going to be everything except for negative 1/4 and positive 1. So that we only have one vertical asymptote here, and that's going to be at negative 1/4. It's going to be like right about here. Let's see, so that'll be x equals negative 1/4. We know that this x equals 1 is actually going to be a whole. So hopefully they ask about that. If not, we'll find it separately. Give the equation the horizontal asymptote. Well, again, we've got degrees that are the same. So we're going to take the ratio of the leading coefficients, 2/4, which is going to reduce to 1/2. So we're going to have y equals 1/2. And that line is going to be roughly here. And then let's see, find all x-intercepts. So we don't have one at 1, we actually have one at negative 3/2. So I'm going to write that as negative 3/2, comma 0. And we can go ahead and plot that. It's negative 1.5. So we've got a point like right here. And then find the y-intercept. So the y-intercept, if I plug in 0 here, 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 and here, I get negative 3 over negative 1, which is at 3. So I do have a y-intercept right here at 0, comma 3. Now, for some reason, this doesn't actually ask us specifically for the hole, but let's go ahead and figure out where that hole would be. So what we will do is we will use what I've been calling the hole equation, which is the equation that you get after canceling out the common factors. So just x, so it would just be 2x plus 3 over 4x plus 1. So the hole is going to be 1 comma something. And then so I'll just say that the hole is going to be at 1 comma something. Let's figure out what the something is by plugging in 1 to our equation here. So we get 2 times 1, which is just 2. Down here we have 4 times 1 plus 1. Okay, so we've got 2 times 1 is just 2 plus 3. So 2 plus 3 is 5. And then 4 plus 1 is actually also 5. Look at that. So it's going to be at 1, 1. So we're going to put a little hole here at 1 comma 1. Right here. Okay. And now we can kind of fill in the rest of the graph here. So we've got this curve going like this, and then this curve is doing something like this. Kind of have to squeeze it in there. So there's a little jump right there at the hole, but generally speaking, this is what it should look like. Complete the night sketch. Yeah, that's it. It's kind of curious that they didn't ask for the hole, but you do need that hole there. So let's make sure we get that in there. All right, let's take a look at the next problem. Number 4, in factored form, you almost don't even need to write it in factored form because we can solve that denominator using the square roots, but it is asking for it in factored form, so let's go ahead and factor it. It's a difference of 2 squares, so my factor should be x plus 2 and x minus 2. So the domain here is going to be everything except for positive and negative 2. So x is everything except for 2 and negative 2. Those are going to be the equations of the vertical asymptotes. And this one does not have any holes because we don't have any common factors between the numerator and the denominator. So we have 2 vertical asymptotes here, one at 2 and one at negative 2. Now in this particular one, the degree on the denominator is bigger here. The degree on top is 1, the degree on the bottom is 2. So that means that my horizontal asymptote is going to be at y equals 0. So I'll plot that right here. Okay, find the x-intercepts. So that's going to be the values that make the numerator 0. So we can see it's just going to be negative 1. So I do have an x-intercept at negative 1 comma 0. And we can plot that on the graph. Negative 1 comma 0. So it looks like we are going to pass through this horizontal asymptote right here. What's next? The y-intercept. We're going to plug, like if I plug in 0 here and here, I'm going to get negative 1/4. So that's going to be the y-intercept. 0 comma negative 1/4. So 0, negative 1/4 is going to be roughly here. So I can kind of see what's going to happen here is I'm going to, like, this is going to be almost looking like a cubic in between these asymptotes, where it comes down, curves over, and then starts going back down like this. Yeah, so let's go ahead and start sketching. So one thing you may have noticed is I haven't done any number lines here, and that's because we've been able to deduce where the graph is going to be based on the information that's given. Now you can always use your test intervals and make that number line to help you figure out if you're above or below the asymptote. But we can just do that pretty quickly by just like picking a number like negative 10 and saying, hey, are we above or below this x-axis? If I plug in negative 10, I get a negative over positive, which is negative. So I know I'm below the x-axis. And then if I plug in a number like 10, positive 10, that'd be a positive over a positive, so I know I'm positive. But there's actually even a quicker shortcut if you thought that was too slow. Since I don't have any multiplicity of these vertical asymptotes here, I know that the behavior of the function is going to alternate as we approach the vertical asymptote from either side. We've seen a couple that like where on both sides of the asymptote it goes up or both sides go down, but that only happens when you have an even multiplicity, kind of like where you have a bounce on an x-axis at an x-intercept. So if you notice that you just have like individual vertical asymptotes and you don't have any repeated ones, then you know it's going to alternate. So you don't have to necessarily do the number line. But making that number line and picking representatives inside your intervals is never a bad idea. It can help you to make sure everything's correct. But this is a complete graph for number 4. So let's take a look at number 5. So this number 5, I can already tell is going to be a little bit of a funky one. I think you're going to like this one. Or hopefully you at least get a kick out of how it's different than all the rest. To write it in factored form, there's not much you could do in terms of factoring, but we can factor out a greatest common factor of 2 on the numerator side. And then right away we say, oh, we've got a factor in the numerator and the denominator. That's the same, so we know we're going to have a whole at x equals -2. Now, -2 is still undefined whether or not it's a vertical asymptote or a whole. So as far as the domain's concerned, it's all real numbers except for -2. But because that -2 is causing a whole rather than a vertical asymptote, there's no other factors to make a vertical asymptote. So when it's asking for the equation of the vertical asymptote, you say, oh, there aren't any. So there's none. No vertical asymptotes. As far as the horizontal asymptote goes, this one's kind of weird, but there is a horizontal asymptote at 2/1. Okay, now, well, I don't want to like spoil it for you, but we'll just say that there's a vertical asymptote at y equals 2. So I'm just kind of laughing because I know where this is going, but you know, you might already see it in your head, but maybe not. Maybe not. I kind of doubt it, but all right. So the last thing here is like find the x-intercepts. All right. Well, we don't have any factors to generate an x-intercept from here, so there's none. Okay. There's no x-intercepts here. No x-intercepts. As far as the y-intercept is concerned, if we plug in 0 up here, we're going to get 4/2, which is 2. So it's kind of weird. Okay, you know, maybe not what you were expecting, but we do actually get a y-intercept of 2 here. Okay, so 0, 2 is the y-intercept, and then it just says, hey, go ahead and sketch the function. You might be thinking, wait a minute, what is happening here? We do have a whole at 2, so let's generate our whole equation. Okay, I think that might help to figure out what is actually going on here. So one of the things about the whole equation is that the graph will look identical to the original equation except the whole is filled in, right? So if I cancel out these x plus 2's, all I'm left with is just y equals 2. Okay, so what I'm going to have is a whole at the x, what was the x value again? -2, so -2, comma 2. So I actually have a whole right here. Okay, -2, comma 2. I have a hole on top of the horizontal asymptote. You don't see that every day. But okay, so like what's going on with the graph here? So remember that the whole equation should look exactly like the original equation except for that hole, right? Well, this is just a constant function, right? Y equals 2, meaning like the graph is just going to be a horizontal line at y equals 2. So this asymptote actually is, except for that hole, the same thing as the graph itself. This is, like I said, pretty unusual. This doesn't happen very often, but the graph here is just going to be a horizontal line with a hole. And that's it. Okay? Doesn't do anything else. So kind of a weird rational function here. But yeah, so it's just a horizontal line with a hole at -2, comma 2, and that's it. Okay? Yeah, so that's it for number 5. All right, so here we go. A summary of what we know so far. How can we find the vertical asymptotes? Okay, so to find the vertical asymptotes, we're going to, so we'll say after checking for holes, we're going to set the denominator. Oh wait, vertical intercepts. Oh gosh, that's a pretty unusual way to call y-intercepts. Okay, my bad. In fact, let's just get rid of that. I don't really like that. Is pretty unusual to call the y-intercept a vertical intercept. In fact, I've never even heard that. I'm not saying that people don't call it that, but it is not very typical. Did that? Okay, no, I still got everything here. Okay, so we're just going to say, how can you find the y-intercepts? Okay, so to find the y-intercepts, we're going to substitute. We're going to substitute 0 in for x and evaluate the expression. Okay, in other words, you plug in 0 and you just calculate it out. Another way of getting it, you could say, or, sort of shortcut way of finding it is just to divide the constants. So like, just kind of going back to one of these before, like if I have my constants is like 1 over -4, I can just divide those because the rest of this is just going to be 0. Either way works. How do you find the horizontal, again, who calls them horizontal intercepts here? Geez, whoever wrote this should really be very questioning. Now, sometimes they are called zeros, so I will give them that. So how do you find the x-intercepts? Okay, so to find the x-intercepts, you're going to set the numerator equal to 0 and solve for x, ignoring solutions which result in holes. Okay, so you don't want to include any x values that would actually be holes rather than the x-intercepts. How do you tell where the vertical asymptotes are going to be? Well, you do kind of the same thing as what you do to find the x-intercepts, except instead of setting the numerator equal to 0, you set the denominator equal to 0. Okay? And just like with the x-intercepts, you're going to ignore any of those x values that result in holes. How can you tell where the horizontal asymptotes are going to be? Well, you're going to compare the degrees of the numerator and denominator. Okay? And then one of three things are going to happen. So if, so let's list out all these cases. If it's, if the degree of the numerator, I'll just abbreviate here, is bigger than the degree of the denominator, then there is actually no horizontal asymptote. I'll just abbreviate this at HA. Okay, however, if the degree of the numerator is smaller than the degree of the denominator, then the horizontal asymptote is going to be y equals 0. And if the degrees are the same, wait, denominator. All right. If they're the same, then you're going to divide the leading coefficients. So y equals the ratio of the leading coefficients. All right, can we get that to fit in there? I bet we can. There we go. All right, so that's how you find the horizontal asymptote. How do you find where the holes are going to be? If there is an x value that makes both the numerator and the denominator the same, equal to 0, there is a hole at that x value. Okay. Take that x value, and, how do I want to say this? Substitute that x value into the whole equation to find the y coordinate. All right, and that's pretty much it. Okay, so really today has just been kind of a review of how to graph these rational functions. Hopefully by now we spent one day just looking at how to find the characteristics, and now we've done 2 days of practice graphing these. You should be getting to a point where you're pretty comfortable graphing any of these rational functions. The homework will just be more practice here, and then we'll have our assessment next time. So y'all have a great day. Let me know if you have any questions or anything. But other than that, I'll see y'all next time.